Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to provide a mathematical proof of a result, of a theorem, if you will. This theorem will be useful to find probabilities when we use the event composition method. Okay? Well, here we go. Let me show you the result, the theorem that we're going to be showing here. It has to do with independence. So what we have here is that if A and B are independent events, then A complement and B complement will also be independent. Okay? So first, we know that we have different ways of showing the independence between two events. This is the one that I'm going to be using here. We know that if two events are independent, the probability of their intersection is the same as the product of the individual probabilities. Okay, so let me write down what we want to show. We want to show that the probability of A complement intersection B complement equals probability of A complement times probability of B complement. We could show the independence in a different way, but I'm choosing to use this one. Okay? We could use conditional probabilities, for instance, but let me use this. You'll see that it's going to work. Okay, so let's begin. I'm going to start from the left-hand side of what we want to show. I'm going to start with the probability of A complement intersection B complement and see what happens. I'm going to try and use properties that hold in general, and maybe at some point I will need to use this, the assumption that A and B are independent. Okay? So first, in general, for any events A complement and B complement, what we have is that the probability of A complement intersection B complement is the same as the probability of A union B complement. And that holds for any events A complement and B complement, right? That holds in general. So I'm not assuming, I'm not doing anything that I shouldn't be doing. Okay, I'm allowed to do that. Okay, let me remind you that we get to do this by one of De Morgan's laws. Okay, this is by De Morgan's law, one of them. Okay, we know that there's another one that has to do with going from unions to intersections. Okay, okay, we're good. Now, the left-hand side, right, is the probability of an event complement, right? The complement of this. We have already shown, right? It's another theorem that we have already shown. We provided a mathematical proof of that result, that for any event, let's call it C, the probability of C complement would be 1 minus the probability of C. Okay? So in this case, it would be 1 minus the probability of the union, right? You guys agree? And in your textbook, that theorem is very important, and they reserved a special number for it. It's Theorem 2.7. But again, let me remind you that we have already shown that theorem in another video. So by Theorem 2.7, and we have already shown that theorem. Okay, we are making progress. Now, that's the probability of a union. Okay? Now, for any union of events A, B, for this union in general, for any A or B, right? The formula that is going to work in general is going to be probability of A union B equals probability of A plus probability of B minus probability of A intersection B. And that is also another important theorem that we have already shown, and that happens to be in your textbook, Theorem 2.6. Okay? Let's keep going. So now I'm going to expand. Okay? I'm going to multiply by a -1 all these terms here inside that curly bracket. Okay, so 1 minus probability of A minus times plus, that's a minus, so I'm going to have a minus probability of B. Then I'm going to have a plus probability of A intersection B. And that's just, you know, we're just doing math, algebra, okay? Okay. Now, have you noticed that we haven't used our assumption, our hypothesis? Our mathematician friends would say that A and B are independent events. Well, guess what? Now, that assumption will be useful here because, well, instead of writing the probability of A intersection B, since these guys are independent, we're going to write the product of A times probability of B, okay? By independence, or let me just say that A and B are independent. And that's by assumption, right? So we have probability of A minus probability of B plus probability of A times probability of B. Are we good? Okay. Now let's try and we're going to try and rearrange these terms so we are able to more clearly see that we're almost there, that we almost have what we want. Let me just think of this guy, 1 minus probability of A, like a single term. I'm going to place this guy inside square brackets. And now let me factor out this probability, this minus probability of B. Okay? I'm going to factor it out. These two guys here, these two terms, if I multiply negative probability of B by 1, I get this term. And then if I have a negative, minus times minus, that's a plus. If I have a probability of A, then that's equivalent to what we have above. Make sense? So this is just, I am placing this guy, I'm thinking of this guy as a single term. That's why I'm placing it inside those square brackets. Then I'm just factoring out this probability of B minus probability of B, and then minus probability of B times 1, this guy, minus times minus, plus minus probability of B times probability of A, this guy here. Okay, now take a look at that expression. Hey, we could factor out 1 minus the probability of A, right? So let me rewrite that expression like this. One minus probability of A times 1 is this guy, this first term, minus probability of B, that is going to be that second term. Can you see that? 1 minus probability of A times 1, this. 1 minus probability of A times probability of B, this. The second term. But now, again, we have already shown, right, by Theorem 2.7 that the probability of A complement equals 1 minus the probability of A complement, right? 1 minus probability of A equals the probability of A complement. And then 1 minus probability of B, again by the same theorem, probability of B complement equals 1 minus probability of B. Probability of B complement. And again, let me just remind you here, so when you check your notes later, you remember that that was by Theorem 2.7, which we have already shown in another video. But now, note what we have done. We started here, the probability of A complement intersection B complement. Well, the probability of that intersection equals the probability of A complement times probability of B complement. And that was, or that is, exactly what we wanted to show. So we are done. Let's summarize what we did. We just showed this, that if A and B are independent events, then A complement and B complement are also independent. And again, from a practical perspective, independence is going to be something desirable for computational purposes, because then you get to find the probability of the intersection, like the probability of a product. Make sense? Okay. Well, that's it. Please take care, keep working hard. See you next time. Bye.